loop powered displays and panel meters that we have available. And again, they also have the capability of working within explosion-proof areas, intrinsic safety areas, and as panel meters inside the panel in the control room. To the left of the meters are a series of PID controllers that we manufacture. They represent everything from a simple PID controller, single loop, dual loop, interactive capabilities. You also have the ability to have manual auto stations and automatic backup stations. In the bottom left-hand corner is a representation of our HART interface modules. HART communication devices can be monitored by the HIM module, which is the one to the far left upper. That device can actually monitor field devices such as multiple input types of devices. And so multi-variables can be read in HART and then represented as either analog outputs in this device back to your control system, or they can become Modbus outputs, and Modbus can be either serial or Modbus Ethernet or any other Ethernet signal. And then the last one is on the far left, and that represents one of the product series that we have in our remote I/O devices. This one is the NCS that has capability of communicating from the field back to the control system, peer to host, and also peer-to-peer communications between devices. They also have the capability of becoming masters. Okay, so that's a quick review of what we do at Moore Industries. Many times when I'm discussing the subject with a group of individuals, I'll ask this question: do you need to measure temperature accurately? Many of the responses are all over the map, but one response I hear often is, no, plus or minus 1 degree is fine for my applications. What this says to me is that many people do not understand how difficult it is to measure temperature to that degree of accuracy. To get to plus or minus 1 degree accuracy in a process environment is extremely difficult. And you would have to do everything right to get to that point. Now, there are processes that need high accuracy temperature measurements, and some that do not need the high accuracy temperature measurements. Just knowing that the trend is going up, down, or staying the same could be sufficient for some. But with many measurements, you may be uncertain exactly what the accuracy is needed. If this is so, then you may ask yourself, do I need to calibrate these loops, and how often? Do I need to verify the performance of the loop, and how often should I do that? Many of the technologies used to develop high accuracy will also result in less drift, like selecting the right sensor for the application, or selecting the right transmitter or I/O device, and by using correct wiring techniques. All of these mean fewer calibrations and less ultimate operating expense. So during this discussion, we're going to look at selecting the best sensor for the application. We'll look for ways to reduce errors via the external environment. We'll reduce error caused by lead wires between the sensor and the measuring device. And we'll look at, can we reduce the error at the measurement itself? So we're going to use an example. In this example, we're measuring the temperature uniformity in this vessel. Operations goal is to maintain the temperature uniformity of the product inside the vessel at 250 degrees F, plus or minus 4 degrees. And we're going to do this by using two sensors. Now, if we use the plant standard, which is J thermocouple, we may not be able to achieve our goal. The ASTM standard notes that the J thermocouple has an accuracy of plus or minus 4 degrees F at 250 degrees. So we could see an 8-degree difference in the two thermocouples, even if the temperatures were actually correct inside the vessel. We could calibrate out the difference, but then you would have to develop a PM schedule to constantly check and recalibrate out the differences. Or, of course, there's another solution. You could select the different sensors. If you were to select a 100 ohm platinum Class A RTD, your possible error would only be plus or minus 0.7 degrees F. Two RTDs could differ only plus or minus 1.4 degrees. The solution is better than the two J thermocouples, obviously. Selecting the best sensor for the application greatly affects the accuracy of the measurement, and it helps to meet the demand of the application's goal set by operations. Not all applications can use accurate RTDs, though. Many applications go beyond limits of RTDs. When needing the use of a thermocouple, look at the accuracy chart for standard grade thermocouples. My example here that I've highlighted is type J and type K thermocouples, and I've done that at 300 degrees and 900 degrees. A J or K thermocouple at 300 degrees has an error of plus or minus 4 degrees F, or that represents an uncertainty of 8 degrees. Or the J and K thermocouple, both at 900 degrees, has an error of plus or minus 6.5 degrees F, and that represents an uncertainty of 13 degrees. Now, you can improve the use of thermocouples by using special tolerance or premium thermocouples. The chart changes a little now. In this ASTM chart, we see that the tolerances for J and K thermocouples are half compared to the standard thermocouple. This is achieved by using wire with a much higher purity of the alloys. At 300 degrees, the J and K is plus or minus 2, and at 900 degrees, plus or minus 3.5 degrees F. You can see the difference. Now let's look at RTDs. If we were to use a 100 ohm platinum RTD at around 300 degrees, we would be using a sensor with a tolerance of plus or minus 0.7 degrees F. Or at 900 degrees, a tolerance of plus or minus 1.9 to 2 degrees F. Therefore, if you think about the past 3 slides that I've shown, you'll note that going from a standard thermocouple to a premium thermocouple cut the possible error in half. Then again, if you go from the premium thermocouple to an RTD, you cut the possible error in half again. So you see that sensor selection is very important for all measurement accuracies. Thermocouples may be wired back to the PLC or DCS at a distance. And when they are, you have to use thermocouple extension wire, which is another source of measurement error. Remember, thermocouples you cannot extend with copper wiring. You must maintain the same type of alloy in the extension wire. Look at the column marked standard error. The J and K thermocouple extension wire adds another plus or minus 4 degrees of uncertainty. Also note that you can buy premium grade extension wire in the other color column, like you can do with thermocouples. Thus, half the error is introduced. The noted extension wire errors are specified for new and pure, unexposed to temperature extremes wire. Over time, the wire also degrades from the process environment and the corrosion effects. So these specs only get worse over time. Do people actually check to see how much error is introduced by a thermocouple extension wire? Most people ignore the aspect of extension wire errors and the loss of stability. It may come up when operations calls and says to point out that the fact that the temperature readings must be incorrect. We know that thermocouples can fail, but thermocouple extension wire can also fail. If you replace the thermocouple extension wire with new wire, then you're just perpetuating the same problem over again. You may have to live with thermocouples, but you do not have to live with thermocouple extension wire. I'm personally a proponent of replacing thermocouple extension wire with other technologies. The other technologies that are used to replace thermocouple extension wire is either thermocouple transmitters or temperature transmitters and remote I/O hardware. Both of these use copper wire to transport their signals back to the control or data acquisition system. You can expect copper to last the life of the plant, unlike extension wire. Modern remote I/O products have similar performance characteristics as modern transmitters and can be at lower cost alternative. When you use transmitters and remote I/O, you still may need to use short thermocouple extension wire between the sensor and these products. It would be best to use premium extension wire and shield it if all possible. And we'll talk about noise in a minute. So, if you individually have not studied the technology of RTDs, but you're aware that RTD extension wiring is just standard copper wiring, you may believe that the copper extension wiring does not introduce error into any of the RTD measurements. RTDs are resistors, variable resistors with temperature. And copper wire also has resistance. So copper wire can cause significant errors in the RTD measurement. In the process plant, there are many contaminants that causes corrosion. And that corrosion causes the lead wire resistance. Therefore, changes in measurement accuracy and stability is in effect. To eliminate the lead wire error, the solution is to use 4-wire RTDs. So let's start with how RTDs are used. What I'm showing here is a 2-wire RTD in its simplest form. In the microprocessor-based world, we measure RTDs by exciting them with a small constant current source. Then we measure the voltage drop across the RTD. We use Ohm's law to calculate the resistance. And then we apply the result to the RTD curve in the microprocessor-based instrument. We read the temperature out as degree F, degree C, or other. The function of the constant current source is to maintain the same excitation current, even though the resistant in the loop is constantly changing. When the industry started using 100-ohm platinum RTDs, they realized that there was a significant error due to the lead wire resistance. This is because we are basically measuring not only the RTD, but the lead wire resistance also. The longer the leads, the greater the error. The solution was to develop 3-wire RTDs. The third wire is added to the RTD, and we're going to make this temperature measurement by using 2 voltage readings, V1 and V2. It is also important to remember that these, quote, voltmeters are of extremely high impedance. So for all practical purposes, there is no current flow through R3, the third wire. Therefore, the third wire's lead's resistance is never entered into the equation. So essentially, the constant current being developed by the source is going down the current carrying lead wires through the RTD and back to R4, back to the constant current source. Since these are high impedance voltmeters, that means that this leg is not drawing any current and therefore doesn't have a draw. Okay? It's essentially not there, except for the fact that it allows the voltmeter to read R1. Okay? Voltmeter number 2 is reading the RTD and R4. Let me cover that in detail. When we measure voltage 1, it gives us the value of the lead wire resistance R1. When we measure voltage 2, that gives us the value of the RTD plus lead wire resistance R4. Then we subtract the 2, and as long as the lead wire resistance is the same in R1 and R4, they each cancel each other out, leaving us with the value of the RTD only. And that would be an accurate measurement, a very accurate measurement, only if R1 equaled R4. In other words, both wires coming from the source of the transmitter out to the field into the RTD and back again, each wire would have to have exactly the same resistance to maintain that accuracy. Though there are too many things working against making R1 and R4 identical in resistance, such as wire gauge intolerance, work hardening that changes wire resistance, and corrosion that constantly works against us. All these causes mentioned contributes to guaranteeing that R1 never equals R4. So if the 2 current carrying lead wire resistances aren't equal, what happens? Well, there is a result to that problem. The result is just 1 ohm of lead imbalance causes 4.7 degrees of offset. If the lead wire imbalance is as little as 1 ohm, I'll say that again, in a 100 ohm platinum RTD, we will have an error of about 4.7 degrees F. If you're trying to measure with the accuracy of plus or minus 1 degree F, as we saw in the third slide, this imbalance between R1 and R4 is standing in your way of success. Since this imbalance may be constantly changing, it would be difficult to calibrate out the error over time. If the imbalance was 2 ohms, the error would be as much as 9 degrees F, and so forth and on, okay? I've seen 5 ohm differences, okay? Then you're over 23 to 24 degrees offset. So there's a solution to this. And that solution is the 4-wire RTD. Now things look a little different here. 4-wire RTDs eliminates the error completely. Remember, the voltage measurement is of high impedance. So for all practical purposes, there is no current flow through leads R2 and R3, and no voltage drop. Therefore, we are only seeing the voltage drop of the RTD itself. I'm losing my voice. So, unlike the 3-wire RTD, we never measure R1 and R4. Therefore, there is no compensation for the current carrying lead wire resistances. So you can see that the voltmeter is directly reading the RTD without reading the resistances of the lead wires. And the 2 wires coming to the voltmeter basically represents a high impedance because the voltmeter is of high impedance. When you use 4-wire RTDs, the lead wires can be of any length. They can undergo constant resistance changes, and still it causes no measurement error. Now, there is one caveat to this that you'll never run into, and that is you cannot have a total resistance that exceeds the drive capacity of the current source. Generally, in our instruments, it's greater than 4,000 ohms. Now, I did a little calculation yesterday on how many ohms how much resistance there would be in wire cable. And standard instrument cable, it comes out to be essentially 40 miles of cable. So the only reason you would have a problem is if you had a sensor 40 miles from, in cabling of 40 miles between your sensor and your measuring device. And of course, that could be 20 because of the 2 wires, okay? So there you go. So with your lead wire error gone, you can go back to focusing on selecting the correct sensor, okay, and the measuring device to further eliminate your error sources. Generally, the only objection to not using 4-wire RTDs is for older legacy measuring devices, such as a 3-wire input card. So older legacy products, especially control systems, would have an I/O card that would either accept multiple types of inputs or just RTDs and an RTD card, and they were designed for 3-wire RTDs at the time. That would be the only reason that in your wiring that you would not use 4-wire RTDs. But we have somewhat of a solution for that too. If the RTDs are right for this application, and if for any reason you cannot use 4-wire RTDs, then you can switch the 100 ohm RTD for a 1,000 ohm platinum RTD. Platinum 1,000 ohm RTDs are quite common. Remember, 100 ohm RTD, we saw a 1 ohm imbalance cause a 4.7 degree error or offset. 1,000 ohm RTD would show the same 1 ohm cause only 1/10 of the error, and therefore the error would be minimized down to 0.47 degrees per ohm. This would be a vast improvement under the circumstances. So you can see 1 ohm of 100 equaled an error of, in this case, in this example, 1.56%. But 1 ohm of 1,000 is 1/10 that. And therefore, the figure 4.7 degrees F turns into 0.47 degrees F error. So that minimizes it. Are there any questions at this point?
Yes, Charlie, I'm not sure if you can see them, but I can read them to you. We do have a few questions
Okay.
over here in the chat box. The first one is, does an accurate type K require a premium type K cable? It's from Mike G.
It doesn't require it, but it would be best to have it.
Okay. Okay, questions are coming in now. Next one, does the length of the extension wire change the error that it causes? I think.
Yes.
Yes, we did answer that one.
Yes.
Another one.
Well, wait. Let
Oh,
me
sorry.
let me expound on that. We're going to be talking about the insertion of noise and error right after this. So you will also see that the length of the wire would give you a propensity for higher noise encroachment. Okay.
Okay. Another one from Mike G. Yes, is the accuracy the TD plus the TC extension wire? 4 plus 4 equals 8 degrees F. This is example.
Well, yes, in a sense. You have to realize that these errors that are calculated by the standards associations, and IEC does the same thing, ASTM, so forth and so on, are calculated on brand new, unused extension wire and thermocouples. And thermocouples in particular degrade faster over time than RTDs do. Okay. So once you start adding up the inaccuracies of each device, including, not only the sensor, but the wiring, and then the transmitter itself, if you're using a transmitter or your IO card, they do add up. Yes.
Great. Another question. As long as I have a 4-wire RTD, will any transmitter work?
Any transmitter that accepts a 4-wire RTD. And all modern new transmitters do.
All right. Next question. Any difference between grounded and ungrounded thermocouples?
Yes. A thermocouple that is ungrounded should have an isolated transmitter associated with it, or an isolated input, number one. A grounded thermocouple will give you a faster response, especially if you're looking at the temperatures inside a metal vessel. The problem with grounded thermocouples is that you can get impingement from other grounded thermocouples in the system. Okay, I've actually seen in the food and beverage industry 2 thermocouples that are grounded that are on 2 sides of the process, and the actual reading back was the average of the 2.
All right. Another question from Chris is, are we going to be discussing thermistors at all
No.
today? Okay. When would thermocouples be a better choice?
Well, in many cases, it depends on the range. So basically, thermocouple RTDs at this time. Well, let's go back in history. If you go back 10, 15, 20 years ago, people thought that RTDs only went to about 850 degrees F. Okay. Today, RTDs are built completely differently than they were in the past. And there's 2 types of RTDs. There are wire wound RTDs, and then there are basically thin film RTDs. Thin film RTDs are basically semiconductor devices. And there are differences in the 2, but the general RTD that people buy today is a thin film RTD. The only time that wire wound RTDs are used is usually for increased stability when you get below 40 degrees F or C. Once you get to that point, you need to use a wire wound device, primarily because it's more stable under those temperature conditions. Okay. Now, the original question again was, when would you use thermocouples? Basically, thermocouple RTDs today can go up to about 1560 degrees, depending on how they're protected. A thermocouple basically will go up to, depending on whether you're using noble metals or base metals, noble metals will go up to about 3,300 degrees. And of course, you're not going to use an RTD at 3,300 degrees. Okay, Thermocouple goes up to just a little beyond 2,300 degrees. It also is very good down to about minus 454 degrees, okay? So essentially, if you go beyond the span of an RTD, then a Thermocouple is always better and required, as a matter of fact.
All right. Question from Pat. Will regular terminal blocks in the wiring path cause errors in measurement?
Well, not if the screws, okay, so are we talking about RTDs?
Sure.
Thermocouple?
Sure. It's unclear, but maybe if there's different.
Okay. Generally not unless you're using a 3-wire RTD and one screw is tighter than the other screw. Essentially, you know, the wire gets hardened over time and the resistance changes. And I've gone to, opened up a transmitter, as a matter of fact, on top of a fractionating tower. And when you opened it up, one screw was tight and the other screw was loose. And essentially, you could see a little white greenish powder around the one that was loose. Obviously, corrosion had impinged upon the environment. So essentially, there was definitely a resistance difference. But I would say, in all practical purposes, if you have the screws both firmly tight and they're protected from the environment, you have less of a chance of a major problem. If indeed it's exposed to the environment, then you have a pathway for corrosion.
Excellent. Okay, we still have a few questions, but Charlie, we'll keep on going with the presentation, okay. And then in our next pause, we'll get to the rest of the questions. But thank you guys. It's great questions. So just when they come up, throw them in the chat box.
Okay, as I mentioned a little bit ago, we'll be talking a little bit about noise at this point, okay? After I take a sip of water. Okay, now let's consider some environmental issues. All of our plants and facilities have VFDs or motors, radios, and of course, normal levels of EMI and RFI can cause errors in low-level temperature signals. Temperature measurements of thermocouples and RTDs are very low-level millivolt signals. When they are direct wired back to the control or data acquisition system, the extension wire serves as an antenna for noise. When that noise gets into the signal, it doesn't take much to mess up a low-level signal. Please be sure that you're using what we call best practices to keep the noise off the wires. Some of these are using drain wires in the bundle, shielding, grounding, and using conduit, and of course, physical separation. Or a better solution may be to convert the low-level signals to high-level signals, like using transmitters with 4 to 20 milliamps, or using the HART protocol and making it digital, or RS-485, or other digital formats, whether it be Ethernet or whatever. And do this conversion as close to the sensor as possible. In other words, it is best that if you are going to do a conversion from sensors directly into an I/O system, that the distance between the two be as close as possible. In this case, up here, you can see the transmitter with one temperature in it, but there is a HART signal imposed on top. So if this is an I/O system that has HART-enabled I/O cards, then it can read directly the HART signal, and therefore you've used a conversion of digital information on top of the 4 to 20 milliamps. Now there's other external influences, and they're shown here. Sometimes we head down the path of convenience and we end up creating temperature errors. These photos show where a long sensor extends from the thermal well out into the ambient conditions. Now, Murphy's law dictates that the ambient temperature will almost always be different than the process temperature, okay? You can see here, there's a thermocouple. It's probably about an 18-inch thermocouple sheath. It probably goes in 3 or 4 inches into the pipe, into the thermal well. It is sealed off with a fitting, compression fitting, and then the wire is extended down on the ground so that people can trip on it. And of course, the thermocouple is sticking out so that if somebody walks by and hits it with their knee, it'll break it off. And then the trip hazard gets placed back over to a pipe stand, probably, where there is a junction box or a transmitter stand, okay? All very inconvenient. Here we're looking at the thermocouple, and we'll assume a thermocouple in this case, going into a vessel, coming out, being exposed to the environment. What is the environment? Is this a steam production area, or is it cryogenic and it's very cold? Into a junction box. So let's see what happens. Basically, there's a temperature gradient along this metal sheet, and the ambient condition is wicking away from the measurement junction. The measurement junction is here at the tip. In the picture on this slide, the ambient temperature is hotter than the process temperature, because the ambient temperature is 102.5 degrees F, and the process temperature is 93, minus 93 degrees. So there is a large gradient difference, okay, in this sheet. Now, basically, the ambient temperature is hotter than the process temperature, and it'll travel down the sheath into the cold process sensor. This will cause an offset error, and it will also develop a long time delay in the measurement response, okay, and inaccurate. Now, there's a solution to this, and the solution is very simple. All we need to do is to make sure that the sensor's measurement sheath is totally immersed into the thermal well. Now, more industries uses a sensor called the worm to solve this and many other issues that happen within plants and facilities. You'll see here, the sheath is about 1 inch or 1.5 inches long. It is pressed into the bottom of the thermal well, so it has good contact. Whether it's a thermocouple, in this case it is a thermocouple, or an RTD, there is a spring loading on this unit. This spring is stainless steel. It is pressing on this unit right here, on the sheath, so that the capsule is pressed firmly against the tip of the internal thermal well. The sheath also protects the wiring. There is a sealed fitting at the end, and then there is a cable going back to your remote I/O junction box or your transmitter. This would be a grip or sealed 1/2-inch MPT device. And the wiring could be protected by, let's say, a stainless steel armored cable, okay? These are standard at more industries and can be used to basically solve the problem that we just saw. Now, if you're looking to purchase a modern temperature transmitter and I/O device, you will generally find out that units with wide range of performance capability among several instrument companies. If you are trying to differentiate some of the specifications between available instruments, you might want to compare these specifications. Now, I'm just going to comment on a few of them, and I've highlighted them. Input resolution. Always strive for the best resolution, because then you'll be able to detect the smallest change in the sensor's output. So high output resolution sees a smaller step change in the sensor. You want to look at long-term drift specifications. Is the measurement of the transmitters, it is a measurement of the transmitter's stability. Okay, and I count that as being very important. RTD excitation current, you want the current to be very low to minimize the self-heating error effect. So self-heating is when you take a larger current and put it through an RTD, which is a resistor, then you're going to actually develop some heat. And that self-heating can give you an offset in your reading. I will tell you that more industries' constant current source in their transmitters is 250 microamps. Okay, very, very small. You want to look at the TC or the thermocouple input impedance. You want the impedance to be very high so that when you're measuring the millivolt signal from a thermocouple, you don't want to draw any current. And you want to look for transmitters that may have advanced diagnostics. Advanced diagnostics can help in predicting sensor failures, sensor drift, sensor corrosion, any predictive faults within a thermocouple or an RTD. Okay. Now, another thing is the measurement device that you're looking at, you want to make sure that it has the ultimate in accuracy. You have to realize that every RTD has a slight error built into it. And there is also a couple of techniques to get rid of sensor error. One of them is sensor trimming. Now, this works for thermocouples also. RTDs, most people that need accuracy will do what we call a bath calibration. So bath calibration technique is used universally. There's also the Callender-Van Dusen equation that basically uses the sensor's constants to be programmed into a transmitter to correct for the inaccuracies of the sensor, thermocouple and RTD. Mostly RTDs though. And the reason is because RTDs is expected to have high accuracy. Essentially, these inaccuracies are caused by the shape of the curve, and that's because of the quality of the alloys being used when manufacturing the sensor. Also, if there's too much or too little metal, it would cause not only an offset, but a change in the curve's position. So you want to have absolute accuracy. You want to do bath calibration as one of the techniques. This is looking at a bath calibration setup. Essentially, you'll see that this is the top of a tank that includes a high-grade oil in it. There is a temperature sensor in there, and the temperature is maintained in the bath at plus or minus 0.003 degrees C. These calibrated sensors get sent back to a testing lab every 6 months. We place the temperature transmitter that the customer is buying inside its housing, its mounting. The sensor is immersed into the bath. Once we stabilize the temperature of the bath, then we modify the curve of the existing sensor to match the ideal curve electronically. Therefore, what you land up getting is basically the ideal curve and the sensor curve match each other. Sensor trimming typically results in a combined RTD and transmitter accuracy combined of around 0.02 to 0.03 degrees F. Okay? So keep that in mind if you need extreme accuracy. For instance, one of my customers is Intel. They make these chips that you use in your computers right now. And Intel uses us for all their accuracy in temperature and humidity. Okay. Now, if you put a temperature transmitter or remote I/O near your sensor, the device digitizes the temperature measurement. If you then send the signal back to the control or data acquisition system via 4 to 20 milliamps, you end up creating 2 more errors. there is a digital to analog error creating the 4 to 20 milliamps in the transmitter. And then at the receiving device, there's an analog back to digital error, basically because because the controlling device or the data acquisition system uses the digital signal. HART protocol is digital, and that's one way to avoid the conversion error. Okay. But you can also use digital communication such as Modbus, serial, or Modbus over Ethernet. That's another option to keep the measurement value digital. Earlier, we saw that using transmitters and remote I/O helped us eliminate errors caused by thermocouple extension wire, and to avoid error caused by noise. Now it helps us by keeping the signal digital and avoiding the analog conversion errors. Using transmitters and remote I/O is becoming a common theme here. So let's take a moment and summarize the practical steps that we can take to improve our temperature measurement errors, and also improving the stability of the measurements and minimizing calibration expenses. 4-wire RTDs eliminate error because of lead wire resistance. Using Class A RTDs and those that have been aged with temperature cycling increases stability. If the application requires thermocouples, use premium grade thermocouples and premium grade noise shielded extension wire. Remember, thermocouple extensions has a finite life, and they degrade the accuracy of the thermocouple measurement. Mount transmitters and I/O as close to the sensors as possible. Avoid having sensor sheath being extended and exposed to the ambient environment. And for accuracy and stability of the measurement to your system, once digital, it's best to keep it digital. So after this presentation, if you wish, by asking Gilson Engineering sales personnel, you can get a copy of Moore Industries Temperature Reference Guide. It's a nice reference book, and the first 26 pages cover many or some of the aspects of what I've talked about today. And of course, if you need anything else, contact your local Gilson Engineering sales and support person if you have any other further questions or need any application help. Are there any other questions?
Okay, thank you. Thank you, Charlie. We do have a few more questions. First one, what kind of accuracy difference can we expect from an isolated versus non-isolated transmitter?
Actually, the specifications are the same. The difference is the impending noise and communications with other devices in an unisolated transmitter. Okay.
Okay. Another question is, why are thermistors not considered a viable alternative? They are cost-effective, accurate, and don't require a powered transmitter if your device accepts them.
Well, what I know about thermistors, being that they're similar to RTDs, except for the way they treat the resistance as the temperature increases and decreases versus an RTD. I do know that in the past, thermistors were manufactured by many different companies, and each company had its own curve. And therefore, it was very difficult to have thermistors that utilized standardization to make it easy to work with. You usually find thermistors in some HVAC applications rather than thermocouples. And more likely, as far as durability and stability, RTDs beat the thermistors out. But you have to realize that when you have the linearization programmed into a microprocessor-based instrument, standardization of the curve is important. And each manufacturer at that time basically had their own variation of the curves. That's how I see it, though.
Okay. This question from Dave. What is the best way to determine how you connect a temperature calibrator for the various types of RTDs?
Say that one more time.
What is the best way to determine how you connect a temperature calibrator for the various types of RTDs?
Well, I'm not quite sure I understand the question in the sense that, basically it depends on the type of calibrator you've got, but as you know, there are several different types of RTDs. There is platinum 100 ohm, 500 ohm. There is platinum 1000 ohm. There is copper 10 ohm. There is nickel 120 ohm. And there may be a few more. Universally throughout the world, platinum 100 is the most used. And if your calibrator has those settings for the type of RTD, then you would hook your calibrator up much as you would with a JOK thermocouple by selecting the readings. Other than that, using a decade box to compare the readings is the other way of doing it.
Okay. Question from Matt. Can you trim a new sensor to an existing transmitter in the field to get an ideal sensor curve?
Well, the answer is you can get closer. And that's by having the digital information using what we call VTD calibration, giving you the constants for each temperature, okay? So we can give you the constants to go into the transmitter, but it's not like calendar Van Dusen, okay, equations. So we can go ahead and use VTD. We can give you the constants for the RTD, what the resistance is, and then you can trim or calibrate your device to that sensor information.
Okay.
Very seldom done though.
Question from Daniel. What's the typical error added by DA to AD conversion?
Well, that depends on the device, and they usually specify that on the devices, okay? It is small, but when added up 2 times, it adds up. I do know that if you take a look at our specs, you'll find that just something like stability figures is based on 1 year, 3 years, and 5 years. And they go from 0.08% of span to, in 5 years, 0.18% of span. The conversion error is small, but when added 2 times, that is conversion from analog, digital to analog, and then analog back to digital, it is additive. I don't have a spec in front of me. It depends on the device.
Charlie, I thought it depended on the resolution, whether it's a 12-bit, 16-bit conversion. And then you take what 2 to the 12th or 2 to the 16th and divide it over the entire range of the thermocouple, and that'll give you your accuracy.
Whether it gives you your accuracy or what the step resolution would be.
I'm sorry, you're correct. That would give you your resolution, which your accuracy can't be better than what your resolution is. It's going to be.
That's true. Absolutely.
That's the way I would answer that.
So our heart transmitters, all except dual inputs, number one, and number two, all of our heart devices are 20-bit resolution, which means that's 1 in 1,400,000 and some thousand. Okay. Basically, 16-bit resolution is 64,556. So now we're looking at greater than 1 in a million. So the effect in a really good temperature transmitter is going to be much less in the conversions than it would be in a 12-bit, 14-bit, or 16-bit device.
Okay, guys, like Charlie said, that's all of our questions, but this temperature reference guide, if anyone is interested, please get in touch with your Gilson sales contact. It's a cool reference guide that is, no cost to it, and a lot of folks do like it. So get in touch with your Gilson representative. We have future webinars coming up as well, so ask to see the list of what's coming down the pipeline. We thank you all for attending, and we look forward to seeing y'all very soon. Thank you, Charlie.
Thank you. Thank everyone.